Okay, 6.9. All right, we want to do some coordinate proofs here. Now, I'm going to give you a hint here. So whenever you're doing these coordinate proofs, when you set up these coordinates, so you just always want to make sure that you do the bigger coordinate minus the smaller coordinate. So basically what you're going to always do is the rightmost coordinate minus like the leftmost coordinate, or you're going to do the top coordinate minus the bottom coordinate. So like if you're calculating slope or distance or anything like that, just always do right minus left or top minus bottom. Okay? So, all right. So what you're also going to find with these coordinate proofs is that you're going to have to like define your own given and prove. So it says prove that the midpoint of a hypotenuse of a right triangle is equidistant from the three vertices. So obviously, if I'm putting a right triangle here, I want to put one of the vertices at the origin, and I'm going to put the right angle at the origin. So then I know that this coordinate right here is 0, 0. This coordinate I could call whatever I want, but it says here I'm going to do the midpoint. I know the y coordinate is going to be 0. Likewise up here, I know the x coordinate is going to be 0. If I'm using the midpoint formula, remember I have to divide by 2, so it's a lot easier just to kind of make this like 2a, and I'll make this 2b. Yes, you could use a and b, but again, in that midpoint formula, you're going to divide by 2, so why not just make your life easier and do 2a and 2b. Okay, so I have to write my given. So I'm going to say given, and I'm going to try to define this as triangle ABC. So given triangle ABC, and I would say that the midpoint, so it's just going to be here, so with midpoint D of hypotenuse AC. And I want to prove that the distance from that midpoint, so I had to give that midpoint a name so I could show that so DA is equal to DC, or CD is equal to DB. Okay, so I had to give that a name so I could show that all those lengths are equal to each other. All right, obviously, so I've got my given and I've got my proof statement. So the first thing I need to do, eventually I have to find these lengths right here, but the first thing I need to do is I need to find the coordinate of the midpoint. So to find the midpoint, again, the midpoint is just the x variables. So in this case I have, like I said, 0. You're not doing a subtraction here, you're just adding, so it's kind of irrelevant, but I'll do top plus the bottom first, divided by 2, and then it would 2b plus 0 divided by 2. So then you would have a comma b. So now I know that d is at a comma b. So now what I want to do is I want to find the distances. So to find the distances, so again, I'm going to do dA. And this is what I was telling you. So when you use that distance formula, always do the, I guess you want to like always do the rightmost one minus the left. You want that to be your first rule. And then like if I was trying to find the distance of AB, which I'm not, then you would do top minus bottom. But just do the rightmost one minus the leftmost one. So I'm going to do A minus 0 squared plus B minus 2B squared. Then for C, again, I'm going to do this one minus this one. So 2a minus a squared plus 0 minus b squared. And then dB would be a minus 0 squared plus b minus 0 squared. So again, I'm just picking the rightmost one minus the leftmost one. All right, so when I do that, I'm trying to show that all these are equal. So here, I would end up with a minus 0, which is just a, so then a squared would be a. Here I'd have b minus 2b squared. Well, so that would give me negative b, but negative b squared is like the same thing as having positive b, because if I square a negative, it's positive, so I'm just going to write plus b. dc, so I'd have 2a minus a, so that would just give me a, so then I'd have a squared. So here I'd have 0 minus b, so 0 minus b is negative b, but then when I square that, I would just have b squared. So far, dA and dc are good. dB, I would have a minus 0. When I square that, I'll get a squared. b minus 0, when I square that, I'll get b squared. So I end up, so I can't, I'm not going to go any further. I can't, like, do any more here. So therefore, dA is equal to dC is equal to dB, okay? So by doing that, I've proven what I wanted to prove. All right, the next one, I want to prove the trapezoid midsegment theorem. This one's going to be a little longer because in that midsegment theorem, 1, I have to show that the midsegment is parallel to the other two bases. 2, I have to show that the midsegment is half of the other two bases added up. So I need a trapezoid. I'm going to put the one corner at the origin. So this is 0, 0. Again, I'm finding a midsegment, so I might as well use those 2's again. So 2a, 0. I don't know, let me just call this A, B, C, D right here. So then C is going to be, if you notice here, like C doesn't line up with anything that I've defined already. Actually, let's go over here and do D first. D doesn't line up with anything I've defined from the X perspective. So I'll just call this, I haven't used, so I'll use B, 2B, and in this direction I'll use 2C. C here doesn't line up with anything, so I need a new X value, so 2D, but the Y height is the same height as D, the way I've set this up, so this is 2C, okay? And then I'll have E over here, and then F over here. Those will be my midpoints. Of course, I'm going to have to find them. All right, so again, given. So given trap A, B, C, D with midpoints of E on A, D, and F on BC. So I want to prove that EF, so the midsegment, is parallel to DC and AB. And then I also want to prove that EF, the length, is equal to 1/2 AB plus DC, or CD, whatever you want to say, okay? So the first thing I need to do is I want to find the coordinates of the midpoints. I'm going to have to find the slope here, so I have to find the coordinates of it. So midpoint, so here's my midpoint work. So for E, I'd have, again, just do right, left. So 2b plus 0 over 2, 2c plus 0 over 2. So E is going to be at B, C. F, again, right, left, 2a plus 2d over 2, 0 plus 2c over 2. So this ends up being just A plus D, this ends up being C, okay? So those are my two midpoints. Let's do the slopes first. So the slope of DC, right minus left, it doesn't matter what the denominator ends up being, it's going to be 0. The slope of EF So up here I'm going to have C minus C, A plus D minus B, again 0. The slope of AB, 0 minus 0, 2A minus 0, so again 0. So these are all the same. So therefore EF is parallel. They're actually all parallel to each other, so DC, and which is parallel to AB. So everything's parallel. Then what I want to do is find all my lengths. So DC, again, do right minus left. So we're going to do 2C minus 2C squared plus 2D minus 2B squared. So this one is going to be 0. This you end up with 2D minus 2B squared, which is just equal to 2D minus 2B. EF, so I'm going to do A plus D minus B squared plus C minus C squared. So here I'd get just A plus D minus B. And then AB, the last one, right minus left, 0 minus 0 squared plus 2A minus 0 squared. So we'd have the square root, this is gone, so we'd have the square root of 2A squared, which is just 2A. So then let me check here. So EF is supposed to be equal to half of AB plus DC. So 2A plus 2D minus 2B. EF right here, I just said it was A plus D minus B. If you distribute that, we get the same thing. So therefore, EF is just equal to 1/2 of AB plus DC. Okay? All right, so on the homework, let me just do one of these proofs with you. So one of 19 through 26. Let me see which one I think is a little bit more difficult maybe. All right, let's do 24. So 24, it says here, so it says up above, use coordinate geometry to prove each statement. So it says one diagonal of a kite divides the kite into 2 congruent triangles. All right. Generally speaking, when you have a kite or a rhombus or something that you want to show that the diagonals are perpendicular to each other, it's kind of nice to put where the diagonals meet at the origin. Obviously, if I have a kite, I'm not going to show that the top triangle's congruent to the bottom triangle. That wouldn't make any sense. So it's going to be the two side triangles. So like I would kind of put it so the axis was here, and then I'd put it so this axis was here. So I'm kind of putting it so this is the origin right here. It's just kind of nice here because then over here, this is 24. Because then over here, you can say that this is like 0 something, you know, this is something 0, this is something 0. Up here, this is 0 something, and this is 0 something, okay? And the kite, these two distances right here are going to be the same. So if I'm 0, so let's say I make this, I made it B, so I'm just going to say it's B. So let's say it's B, and this is negative B, because the distance from the origin are the same. If I go up here, I'll just call this one A. This distance down here in the kite, so it's not going to be the same distance away. If it was a rhombus, they'd be the same distance away, but it's not. So this is going to be, I'm just going to call that one C. So I think I labeled this A, B, C, D. So I'm starting off by saying I'm given kite A, B, C, D, and I want to prove that triangle ADC is congruent to triangle ABC. Like I said, it wouldn't make any sense to prove the top and the bottom are congruent. That wouldn't work out. Okay, so to prove triangles are congruent, we could do side, angle, side, 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 side. You could do angle, angle, side, angle. Well, here's the problem. You're not going to be able to figure out the measures of any of these angles. So the only one that you're going to be able to do in a coordinate proof is side, side, side. So we need to show that all the sides are congruent. Now, this one, AC, is the reflexive side. Like, AC is congruent to AC by reflexive property of congruence. So I'm good there, that's fine. But for AB, I need to show that it equals AD. So AB would be, again, that distance there I'm finding. So I'm going to do the right one minus the left one. So B minus 0 squared plus 0 minus A squared. So I end up with B squared plus A squared. Okay? Again, negative A squared, the negative times the negative makes it a positive. AD, again, if I do right minus left, 0 minus a B, minus a negative B is going to be plus, and then A minus 0. So again, here I have B squared plus A squared. So this right here tells me that AB is congruent to AG. Okay? I'm going to do the bottom parts now. So DC, again, I'm going to do right minus left. You know what, just forget what I said earlier about top minus bottom. That's not really true. Always just do right minus left. So 0 minus a negative B is 0 plus B. C minus 0. So I'm going to have B squared plus C squared. And then if I do BC, so again, I'm going to do right minus left. So B minus 0 squared plus 0 minus C squared. So then I end up again with B squared plus C squared. Remember, this would be like negative. So yes, 0 minus C is negative C, but when I square a negative, I still get a positive, so that's why I'm just writing it like that. So then this tells me that DC is congruent to BC. If you notice here, I'm putting the segment notation there when I'm talking about congruent, but when I'm finding the length, I'm not putting it there. So then I know that triangle ACD is congruent to triangle ABC by side, side, side. Okay? So that's that.